Welcome to this explainer. If you've ever stared at a chemical equation, you might have thought it was just a random jumble of letters and numbers. But actually, it's far from it. It is this highly logical, completely secret language that literally decodes the physical world around us. Today, we're diving right in to crack the exact code that dictates how the universe transforms. Okay, let's take a quick look at our roadmap. We are going to start with chemistry's secret language, then we'll move into the art of balancing, explore the reaction playbook, understand redox reactions, and finally, look at chemistry in everyday life.
All right, let's kick things off with Section 1, Chemistry's Secret Language, and specifically, the vocabulary. Now, to even begin to read this language, we first need to understand the transformation itself. A chemical reaction isn't just mixing things together, it is a profound shift. The starting materials, the reactants, literally lose their original identity. They are completely unmade and remade into entirely new substances with entirely different properties. It's wild. And the chemical equation? Well, that's just how we document this physical shift.
To do this efficiently, chemists use these brilliant shorthand cheat codes to pack massive amounts of information into tiny letters. Think of them like the emoji tags of the physical world. A little S, L, or G tells you if something is solid, liquid, or gas. Got an AQ? That stands for aqueous, meaning it's dissolved in water. If you spot an upward arrow, that indicates a bubbling gas escaping, while a downward arrow means a solid precipitate has suddenly dropped out of the solution. Oh, and if you see plus heat over on the product side, that means you've got an exothermic reaction. It's giving off heat.
Moving right along to Section 2, the art of balancing, or as I like to call it, the cosmic scales. Here is the thing about the universe. It absolutely demands perfect balance. A skeletal or unbalanced equation is essentially just a rough draft. Sure, it tells us what is reacting, but it actually breaks the laws of physics. Why? Because the number of atoms don't match up from start to finish, which implies that matter was magically created out of thin air, or just vanished. Reality requires a balanced equation. The atoms of each element on the reactant side must perfectly equal the atoms on the product side, no exceptions.
So how exactly do we fix a skeletal equation? Well, we use a form of cosmic accounting called the hit and trial method. It's like a giant puzzle. First, you hunt down the compound with the biggest formula, or the element that shows up in the fewest places. Then, for step 2, you start multiplying those symbols by small whole number coefficients. Putting a 2 or a 3 right in front of the molecules. And then you just keep tweaking. Step 3 is continuing that process until the atomic books are perfectly equalized on both sides. It takes a bit of trial and error for sure, but it's highly logical.
Next up is Section 3, the reaction playbook, focusing on how these chemical interactions actually play out. When chemicals interact, it might seem completely chaotic from the outside, but it actually falls into 6 very neat, predictable plays. Combination merges 2 things into one. Decomposition breaks one compound apart, often triggered by adding heat, light, or electricity. Then you have displacement, where a more active element kicks out a weaker one, and double displacement, which is essentially a partner swap. If that swap creates a solid that falls out of the liquid, boom, that's precipitation. Finally, neutralization. That's the classic battle where an acid and a base completely cancel each other out to form harmless salt and water.
Now, to truly grasp those displacement reactions we just talked about, we have to look at the activity series of metals. This is the ultimate hierarchy. It lists metals in decreasing order of reactivity, starting from highly reactive potassium all the way at the top, down to totally unreactive platinum at the bottom. In chemistry, it's a tough world. A more active element will ruthlessly displace a less active element from its compound.
And the absolute crucial threshold here? Hydrogen. Any metal sitting above hydrogen on that reactivity list, like zinc or iron, will attack an acid, steal its place, and force hydrogen gas to bubble away. But if you look at metals below hydrogen, like copper or gold, they will just sit in that acid completely unharmed, no reaction. This one single rule dictates exactly how we safely store dangerous chemicals and which metals we choose for our critical infrastructure.
That brings us to Section 4, Understanding Redox Reactions, diving into dual transformations. All right, get ready for chemistry's ultimate dualities. Oxidation involves gaining oxygen, losing hydrogen, or losing electrons. Reduction is the exact mirror image. It's losing oxygen, gaining hydrogen, or gaining electrons. The absolute critical takeaway here? They always occur together. If one substance loses an electron, another substance absolutely must gain it. One literally cannot happen without the other. They are a package deal.
So, knowing that, here is a bit of a brain teaser regarding the agents involved. An oxidizing agent is the substance that gives away oxygen or takes away electrons. But because it's taking electrons to cause oxidation in something else, the oxidizing agent itself actually gets reduced. Conversely, a reducing agent causes reduction by giving away its own hydrogen or electrons, which means the reducing agent itself gets oxidized. It sounds backwards, but an agent always experiences the exact opposite of the reaction it causes. Finally, Section 5, Chemistry in Everyday Life. Let's take the macro view and see why all of this actually matters to us. We have all seen oxidation out in the real world. We usually call it corrosion. Atmospheric gases, like oxygen, attack different metals in vastly different ways. When iron corrodes, it undergoes oxidation to form hydrated ferric oxide. You know it as rust, and it flakily eats away at the metal, destroying it. But interestingly, when aluminum corrodes, the oxidation creates a super tough outer layer of aluminum oxide. So instead of destroying the metal, the reaction actually forms a protective shield. Because rusting iron is so incredibly destructive, we've had to engineer chemical countermeasures. We block oxygen and water vapor by doing simple things like painting or greasing the surface. Or we can look back at our activity series. We can coat iron with a protective layer of zinc, a really cool process called galvanization. Or we can electroplate it with tin, chromium, or nickel. We are literally applying our knowledge of chemical reactions to keep our bridges standing and our cars from falling apart. And guess what? Oxidation also attacks our food. You know that terrible, stale smell from an old bag of chips you left in the pantry? That is rancidity, literally the oxidation of fats. Food scientists fight back using antioxidants, refrigeration, and vacuum packing. But my favorite method is nitrogen flushing. Next time you complain that your fresh bag of chips is mostly just air, remember, it's actually unreactive nitrogen gas. It's deliberately pumped in to displace the oxygen and stop the chemical reaction of staleness. We are using chemistry to fight chemistry. So there you have it. We have decoded the secret language of the universe. We've balanced the equations, explored the chemical playbook, mastered those tricky redox dualities, and seen exactly how all this saves our infrastructure and our favorite snacks. You are no longer just looking at boring letters on a page, you are observing the fundamental rules of transformation. So I'm going to leave you with this. Now that you actually know the language and can see the code, what other invisible reactions do you think are perfectly balancing themselves around you right now? Keep observing, keep questioning, and I will see you in the next explainer.